This video follows on from the one where I talked about representing instructions as strings of binary digits. Now I'll extend that to programs, sequences of instructions, and talk about the overall architecture of the instruction set of the computer. The overall structure of a computer has three parts. It's got the central processing unit, the main memory, and the input-output devices. Here's a picture of how we might draw the overall structure of the computer. The CPU, the central processing unit, is the part of it that does all the calculation and the hard work, and it gets its data from the memory and it stores its results in the memory. But of course, this has to communicate with the outside world in order for humans to interact with it. So it also has connections to input-output devices. The main memory part of this is very simple. It's made up of these bits, these binary digits, and it's structured usually into 8-bit sequences that we call bytes. You may have heard that term, the byte. And the computers of today, of course, have very large numbers of bytes in their main memory. A typical computer might have multiple gigabytes, 4 gigabytes, 8 gigabytes, or a lot more. The bytes, they're laid out sequentially in the memory, and they're each given a number. So you can address them, so you can select one. So the first byte is in fact what we call the 0th byte. You start from 0 in computers. The second byte is going to be byte number 1, and then byte number 2, 3, 4, 5, and so on. These numbers are what we call the memory address. So if I want to find out the value of a byte, I just quote the memory address and ask the computer to fetch that particular value of the byte, and it picks it up. If I want to store something in the memory, then I use the memory address to tell it where I want to store it. So here's a simplified picture. You lay the bytes out in the memory sequentially, and we give them these addresses. So 0 is the first one, 1, 2, 3, 4, 5, and so on, right up to the last byte in the memory. Input-output devices are the next major part of the computer to talk about, and output devices accept a stream of bytes from the CPU to be presented to the outside world. So, for example, they might represent patterns that appear on a screen. They might be character patterns. They might be shapes, colors, whatever. That's an example of output. On the input side, you have things like a keyboard or a mouse, and the keyboard will generate bytes which are received by the computer and stored into the memory. We also have devices, input-output devices, that take bytes and store them for later use. Another form of memory. These are the so-called mass storage devices. They're typically much larger than the internal memory of the computer, and the cost per byte is much lower. So, for example, disk drives might have terabytes. These days you can easily buy a multiple terabyte disk drive for $100. And this is where we store data when the computer is switched off. Because normally when the computer is turned off, the data in the memory disappears. When you turn it back on again, what's in the memory, the main memory, is some sort of random sequence of bits. So in order to save results and information between turning the computer off and back on again, we use a device like a disk drive, a mass storage device. And this is another example of an input-output device. The CPU sends bytes to the disk, it stores them at some location on the disk that you specified, and you can read them back as well. And there are many types of mass storage like this. So here's a picture. We've got our CPU and memory. They're sort of internal parts of the system, and connected to it are the keyboard as an input device, the screen as an output device, and there on the left I'm shown an icon for a disk drive, which is like a two-way device. You can store things there and you can read things back. Now, the central processing unit is the most complicated part of the system. The CPU takes bytes from the memory and, as we've seen in previous videos, can interpret those bits as instructions and carry out what the instruction specified. So the instruction might do things like add two numbers together, multiply numbers, do all sorts of arithmetic or logical operations. Or the instruction might be to send a byte to an output device, or send a whole sequence of bytes to an output device. The CPU faithfully interprets these bit patterns as instructions. So here's a picture of how this might work. You've got your memory there with the memory addresses containing bytes which can be interpreted in many ways, but the CPU will read them in, interpret them as instructions, and carry out the instruction. Now, if we look inside the CPU to see what it consists of, there are basically three major parts. There is the control unit, which is digital logic that decodes the instructions and works out what to do. There's something called the arithmetic and logic unit, which does arithmetic operations like addition, subtraction, multiplication, divide, and so on. But it also does logical operations like and or. And it will carry out these on any of the data that's presented to it by the instruction that the CPU is executing. And lastly, a very important part of the CPU are registers. Registers are where we store intermediate results. Registers are small and fast memories, just like the main memory, but they only contain a few bytes, and they're generally much, much faster than the main memory. The main memory is a fairly large store, can be gigabytes. The registers are very small. Each register might contain 4 or 8 bytes or more, but typically they're fairly small, and there are only a few registers. We might have 32 registers, 64 registers, and so on. Or in some very small machines, there might only be one, or there might be two. The instructions move data from the memory to the registers and carry out the arithmetic and logical operations on the data in the registers. So we have the control unit there, which is what we call combinatorial logic, digital logic, that interprets the bit patterns from the memory, reads and writes data into the registers, sends data to the ALU and gets results back, and so on. The control unit manages all of that. Some of the registers have special functions. The most important one of these is something we call the program counter. This is basically a register that contains the address of the instruction that's being executed. The CPU has to know where in the memory to find the instruction to execute, so it uses the value that's stored in the program counter register as the address to look up to fetch the next instruction. Now, it gives you the beginning of this sequence of bytes for the instruction, because an instruction might actually be made up of several bytes. When the instruction is completed, the program counter is incremented by the right number of bytes to get it to the next byte in the sequence, and the process begins again. The CPU will then fetch the next instruction from the address that the program counter specifies and carry out the next instruction, and so on. So here we have our main memory, and we've got the program counter, usually abbreviated to PC, and it contains the address of this next instruction. And the CPU will use that address to fetch the next instruction and execute it. Now, as I said, registers in a computer, there may be several of them. You've got your program counter, and in this particular diagram I've shown 4 registers. They're numbered usually, and we call them R0, R1, and so on. By numbering them, it means it's like an address, and so we can use 2 bits to select a particular register here, from the R0 to the R3. The PC is usually a special register. It's made out of the same technology, and it's very fast and so on, but it normally doesn't fit into the list of general purpose registers. The general purpose registers are where we carry out arithmetic and logical operations and that type of thing. Now, as well as arithmetic and logical operations being carried out in registers, registers are also used for testing, to be able to see if the result of some operation is 0 or greater than 0 or less than 0 or something like that. And so it can, the CPU can then decide which instruction to execute next on the basis of the value in the register. So, just looking at a typical sequence of instructions that might involve registers, here we've got a load instruction that loads the contents of location or address 1000 into register R0. Then it loads the contents of location 1004 into R1, adds R1 to R0, and then stores R0 into location 1008. Now, I made a few assumptions here. First, I'm writing these instructions in assembly language. I mentioned assembly language in an earlier video. This is just a convenient, easy to understand for humans shorthand for instructions. The real instructions are, of course, the binary codings of these. But this assembly language maps directly onto the instruction code. So the load would be some particular bit pattern. Then there might be a bit pattern to represent which register to load into, and then the bit pattern for the address. But that's a bit opaque for a human to look at, so we write it using these nice mnemonics like load and add and store and so on. The other thing about this is that I'm assuming that operations in this particular computer operate on 32-bit quantities, not just a single 8-bit byte quantity, but a 32-bit quantity, and a register is 32 bits long. And that's why you might notice that I've got the addresses not going 1001 to 1002 or something like that. They start at 1000, then the next one is 1004, and so on. So they're 4-byte chunks, 4 bytes being 32 bits. So when we have an instruction like load R0 from location 1000, what we're doing is taking the 4 bytes starting at 1000 and putting them into the 4-byte register or 32-bit register R0. And the same for the store operation. The add operation here in my sort of mythical made-up computer adds one register to another. So it adds register R1 to register R0 and leaves the result in R0. Now, all these examples that I've shown you address the memory with an explicit address stored in the instruction. So load R0 1000 specifies the address to load from in the actual instruction. But most CPU architectures have the ability to use a register to contain the address or contain a number to use as an offset to an address when you're fetching a value. So for an example, we might have an instruction to load register R0 from address 1000 offset by the value in register R1. So here's an example of that. If we do I've called it load I for load indexed, or using an offset, load I R1 R0 1000. That means in my hypothetical computer that I'm going to load into R0 what's at location 1000 plus the number in R1. So if R1 contained 4, for example, then the address it would actually fetch from is 1004. This is called indexed addressing, and sometimes we call registers, when they're used in this manner, we call them index registers. So here's my example. We have the main memory, we've got location 1000, we've got our index register, the contents of the index register is added to the location 1000, which was in the instruction, fixed in the instruction, and the offset then gives us a resulting address, which is used to fetch the value to put into R0 for my instruction. Now, another way of doing this is to, in fact, make 0 the address in the instruction, and then you can put any address into R1 and use it to access anywhere in the memory. So the offset is essentially the address, and in the instruction we store the value 0. Now, these index operations are great for accessing arrays. Now, an array is a sequence of memory that we index into in a high-level language, and this is implemented using these indexed operations, because in the instruction we could put the address of the beginning of the array, and the index could be stored in the index register. and that would allow us to select the particular value from the array in our implementation in the machine code. So here's an example. So we've got our array start here. We've got the index value for the array that stored in R1. They're added together to give us the final address to fetch the value from. Now, if all our programs were just a sequence of instructions, then we couldn't write very interesting programs. They'd just be one long sequence: do this, do that, do something else. Programs become much more useful and interesting, but more complicated, if we have branching, if we have some way of testing the result of a value, and as a result of that, doing one thing or a different thing. And there are instructions that let us do that. I've already mentioned the idea of testing a value that's the result of an arithmetic operation. And so there are instructions which will test the value, see whether it's 0 or greater than 0 or less than 0 or something, and then jump to another location if the test is true, if it is greater than or whatever, or continue operation in the sequence if it's not. And this allows us the equivalent of a high-level language if statement. So here's an example where I've got a load instruction, loads the value from address 1008 into register R0. And then I've got another hypothetical instruction from my hypothetical machine. I've called it jump Z, which will jump if the value in the register R0 is 0. And if it is 0, it will then continue execution at location 2000. If it's not 0, it will just continue execution at the very next instruction. So here's a really simple way of implementing an if statement from a high-level language in our hypothetical assembly language or machine code. The other thing that we can do is we can do indexed jumps. So we might decide to have a variable place to jump to, and have a switch or a jump table, as they call it, to allow you to select many different places to continue execution depending on the value. This is used for implementing things like case statements or switch statements in high-level languages. The last major operation I want to describe that is in most instruction sets is the ability to do function or sometimes called subroutine calls. This is where we have another piece of code that we want to call. If you know a high-level language, you're very familiar with this. We want to call a function and then return from it when we've finished. And we want to get back to the place just after the call. And your function could be called from many different places in your code. So you can't hardwire the return address. It has to depend on where it was called from. The other thing we would like to do with functions is we want to allow one function to call another function, and that function to call another one, and so on. But as they return, to always come back to the right place, and then come back to the place before that, and so on. So in other words, have nested function calls. Now the way we implement that in our machine code is with a concept called a stack. Now this is very simple. A stack is just an area of memory, a sequence of bytes, where we store values and we only add them to the end, or as we call it with the stack, we add them on top of the stack. All right, and if we want to remove something, we only remove it from the top or the end of this area of memory, and then we then make the new top of the stack one less, and so on. So we use this to store the return addresses for functions. So when a function is called, the return address is placed on top of the stack. It's placed at the end of this memory area. And we have to have a pointer or a register which shows us where the current top of the stack is. And that's increased when we want to put something on the stack, and we put the value on. And when we want to return from a function, we pull the current top of the stack, or the last one, and we reduce that value in the stack pointer. This can also be done the other way around. Sometimes a stack might grow downwards in the memory and sometimes upwards. But it's always a contiguous sequence of memory and depends on being able to increment or add a number to the stack pointer, to the register pointing to the last part of the stack, in order to manipulate the stack. We sometimes call these operations push when we put something on top of the stack, and pop when we take something off the stack. And this is how we make nested function calls. So here's my diagram. My R1 I'm going to use as my stack pointer. It points to the current top of the stack. We also have to know where the base of the stack is, and to add something to the stack, we increment the stack pointer, increment R1, store something into that location, and you know how to do that because we know about indexed addressing, and then on you go. And when we want to return, we would use the current top of the stack, that address from R1, as the place to find our return address. But before we actually return, we reduce the value in R1, and so it now points to the new top of stack, and then we return. So very straightforward, and this is the basis for all function calls and so on in high-level languages. So this has been a real whirlwind tour and introduction to instruction set architecture of computers. I haven't described any specific CPU type. I've used a hypothetical CPU because there are so many out there, and they all have a very similar top-level architecture in that they've got instructions, they've got registers, they've got arithmetic logical units, they've got function call stacks, and all that sort of thing. So the idea was to introduce you to the concepts. But the main thought is I want you to take away the idea of how we could write a sequence of instructions to implement a program inside the computer. And everything in computing is then built on this foundation.